everyone, my name is Chenxing. So today I'll briefly talk about thermal elasticity. This is a project we collaborate with these other people from China. So in today's talk, I'll first go through some background of why we are interested in thermal elasticity. Next, I will show you how to calculate static elasticity. After that, I will briefly review the semi-analytical CIJ method, which is used to create the code and perform thermal elasticity calculation. After that, I will show you how to use the code and some examples. At the end, I will briefly summarize. And after that, I will probably show you how to actually run the code in the computer. So the reason why we are interested in thermal elasticity is because the elastic tensors, or CIJ, could, as a function of pressure and temperature, can be used to calculate acoustic velocities. And in our case, we are interested in geophysical insights, which means that if we calculate the elastic tensor of minerals, we calculate the acoustic velocities of minerals. And by comparing the minerals' acoustic velocities with seismic observations, which are the seismic wave speeds in the Earth, we are able to understand what's inside the Earth or the chemical compositions. However, despite recent developments, it's still very challenging to actually measure the elastic coefficients. Because there are really high pressure and temperature measurements that are very difficult to obtain. So therefore, we are interested in doing this using ab initio methods. However, as Renata have said, the traditional method to compute elastic tensors are still very expensive and time-consuming, and it's very difficult for people to manage these files. For example, if you want to obtain the elastic tensor at a specific pressure and temperature, we need to shrink the crystal at that pressure and temperature for 12 times and perform molecular dynamics on those configurations. And if we want different pressure and temperature, we need to do that at 12 times the number of pressure and temperature points. So this is very difficult. So what this method does is we reduce the effort to obtain this thermoelastic constant by we only use the phono and static elastic coefficients, which I will show you in the next few slides. And that was all we need to obtain this high pressure and temperature elastic coefficients. This is basically some approximation made on top of the quasi-harmonic approximations. So this method was developed by this paper, 2011 as alternatives. And our predictions have shown some very good agreements with compressed minerals in the experiments. So next, I will show you how to perform static elastic calculation. Static elastic coefficients are calculated using the stress versus strain method. Or in other words, this is just a Hooke's law. If you have if we strain the system, for example, like we strain the method on the A direction, and if we call that string E1, and we obtain the stress change, we can use this relationship to observe CIGKL. And more detail is like this. So assume we stress the crystal. If we stress the crystal, that is if we stress the crystal in the A direction and apply the strain of 1%, and that is like this. After the strain, the elastic coefficients were changed. Assume the original crystal coefficients is A naught, like this, A naught 1, 1, A naught 2, 2, and A naught 3, 3. This is orthorhombic crystal. And to apply the strain, we multiply this matrix by this string matrix that is 1 plus this string. And we have the crystal after the this is the lattice parameters after the change. That is the 1, 1 direction is stretched by 1.01%. 1%. So, and we can calculate the stress. We can calculate the stress change from sigma naught to sigma naught plus this change. And if we use the Hooke's law to calculate what we expect it to change, that we will have this tensor, the CIGKL times the original epsilon 1. And what we get is this. Then we compare the term from each of these tensor terms with this what we get from our initial calculation. And then we will obtain from C11 to, actually this is C11 to C12 and C13 and C1 something, all these terms. And if we apply the strength from epsilon 1 to change epsilon 2 and epsilon 3, we will obtain all the elastic coefficient terms. And that is how we solve for this elastic coefficient tensors. And in practice, we will apply a pair of positive and negative strings to make the calculation more accurately. And for the semi-analytical method, we will be based on the it is defined in terms of the free energy quasi-harmonic method. Here on the left, I'm showing the elastic coefficients defined as a second-order string derivative of the free energy. So under the quasi-harmonic method, the Helmholtz free energy is shown like this. So besides the static terms, the rest of terms are a function of are written in terms of the phonon frequency, which is only a function of volume. So in order to evaluate this string derivative of the free energy, what we need to do is to evaluate the string derivatives of the frequency shown here. So how we do that is we use the string coordination method. We use the string coordination parameter, which is this gamma QMIJ. This is the string coordination parameter, mode string coordination parameter, which is the derivative of the ln frequency. So what this semi-analytical method do is to approximate everything with the products of the string coordination parameters and string derivatives of this. And it also applies an approximation with the average coordination parameter to connect the average coordination parameter with the mode coordination parameter, which is defined in terms of each mode. So here I'm showing you some expressions for the average coordination parameter and average product of the coordination parameters and average of the string derivative of the coordination methods. Everything was connected to the mode average using this is the actual compressibility. So there are more specific expression for the shear and off-diagonal terms. I'm not going to show it here, but they are basically all solvable by applying a rotation in the crystal axis. And in this code, we provide a general solution for all the crystal systems. They are demonstrated to show that they are in good agreements in different crystal systems. So to use the CIJ code, it is actually pretty easy. So we have published the code to the Python's package index, and if you want to use it, you will just need to do a pip install, and that is CIJ. And we have also published online documentation that is available here. To initiate a semi-analytical method, you will just run the following command, CIJ run, then the settings is the name of the calculation settings file. Throughout the program, the code will first read the input and perform quasi-harmonic approximation. After that, it will interpolate the frequency versus volume and calculate the coordination parameter and calculate the string derivatives of the coordination parameter. After that, we were able to calculate the phonon contribution or thermal contribution to the CIJ. After that, if we put together the static part and the phonon contribution, we obtain the CIJ versus volume and temperature, and also the adiabatic ones. And using these elastic coefficients at high pressure and temperature, we are able to calculate the bulk shear moduli and velocities. After that, we can generate the output. So for a single calculation, we will need a calculation settings file and two other files. The one is the quasi-harmonic approximation input and the static CIJ data. And here, with this command, it will run the settings file. And in the settings file, we specify the location of these input files, and the calculation can be calculated. To prepare these input files is actually pretty easy. So you specify in the first section is the quasi-harmonic approximations settings, where you specify the location of this first input file and some inputs, including the definition of the pressure and temperature grid to obtain the equation of state. And in the second section is about elastic coefficients, where you specify the name of the second file, which is here I name it input 02, but actually if we have these files, it will be elast.dat. And also some settings, including the symmetry of the system, where you wouldn't have to specify all the elastic coefficient terms, but only the individual, only the linear not related terms. And also how you want to interpolate the frequency as a function of volumes. And finally, you specify the output. For example, you need the elastic coefficients and book and share moduli and some velocities. The next file is the QJ input data. These are very similar to what you will need to perform a quasi-harmonic approximation. In the file, first you specify the number of volume, number of moles, number of Q points, and number of moles at each Q points. The number of molecules and number of atoms. After that, you specify the pressure, volume, energy at each volume points and the corresponding Q points and their frequencies. And after that, you specify the second Q points and frequencies. And after all the frequencies, after all the Q points are listed, you move on to the next pressure points. And at the end, it will be the weights of these Q points. These are very similar to QJ input. And the third file is the static CIJ data, where you specify the volume, number of volumes, and the mass, which are used to calculate the velocities. So after that is a list of different volumes and the CIJ at this volume. For example, the V1 and the C11 at V1 and C22 at V1, and so on. After that, you have a list of lattice parameters, and these were used to calculate the actual compressibility. And CIJ, so if you type in CIJ, it will show you some, it will show you the available commands. So besides performing the thermoelastic calculation, we are also able to calculate static elastic coefficient, which is basically an interpolation. And we are able to obtain a table at a specific pressure and temperature from the results. And we have also some utilities tools to help you deal with the static elastic coefficient. For example, to fill the non-zero terms based on the original, based on the crystal symmetry, and some tools to plot the results. I will show you some 3 examples, which I will try to run after this talk. These are 3 different systems from 3 different crystal systems. The magnesium silicate bridgemanite. This is the most abundant phase in the Earth, and this belongs to the orthorhombic system. For the orthorhombic system, we have 9 elastic coefficient terms. So in this slide, you will first calculate the equation of state as a function of pressure and temperature. On the top left, this is there we have some experimental measurements. You can see they agree quite well with our calculation, and this lays a solid foundation for further elastic coefficient calculation. And this is another figure showing the volume as a function of temperature. On the bottom right, this is the expansion coefficient. This boundary calculated using the second order derivative of the volume versus, this is the second order derivative of the expansion coefficient as a function of temperature, which defines where the quasi-harmonic approximation is valid. So we are, the quasi-harmonic approximation is basically valid below this temperature range. So after that, you're able to run the code and obtain the C11 to C66 as a function of pressure and temperature, and compare with this is also molecular dynamics calculation, but you can see they are in quite good agreement, which shows that this approximation works well, even if we simplify it a lot. There are not many measurements because the measurements is still too expensive for the system, even for the most abundant phase in the Earth. However, if we but there are more measurements on the book shear moduli and also the book and the compressional and shear velocities shown here. So you can see both the temperature dependence and also the elastic coefficients are in quite good agreements with these measurements. And book and shear velocities are calculated using this method. Use these equations. Yeah. And the book and shear moduli are calculated using the Voigt-Ross-Hill averages, which I think I don't have the expression here. In the next example is diopside, which belongs to the monoclinic system. As you can see, there are more examples here. It has certain independent elastic coefficient terms, and we have more measurements. And here in the example, you can see in low temperature, they are in better agreement, and after we reach the quasi-harmonic approximation boundary, they are in less good agreements here. And this is also how if we calculate the book shear moduli and the VS and VP, and the results are in good agreements with us. And last one is Akimoto height, where we have this relationship. This is the equilibrium states, and this is the
dioxide.
Yeah.
Oh yeah.
Akimoto height, and this is the QH boundary and thermal expansion coefficient. And this next slide shows the individual elastic coefficient terms. And finally, the book shear moduli and velocities. So in conclusion, we introduced this Python package CIG that it calculates the thermal elastic tensor and acoustic velocities. And in this code, all the input we need is the phonon frequencies and the static elastic coefficient, which will greatly reduce the the cost of calculating the thermoelastic coefficients. The code implements the semi-analytical CIJ method and has been successfully tested on many systems and different symmetries. So next, I'm going to show you this code in practice.